Hello everybody. My name is Tanguy Ophoff and I will be presenting the work that EAVISE has been doing this last year for the OmniDrone project. EAVISE's goal within the OmniDrone project has always been to design faster and smaller object detection networks so that they can run in real time on our embedded devices without deteriorating the accuracy. In order to solve this challenging task, we start from the key idea that there's a big difference between academic datasets and industrial datasets. Looking at academic datasets, you can see examples like Pascal VOC, which contains 20 very different classes, going from cows to persons to planes to TV monitors, etc. There's also RGB images as well as grayscale images. The viewpoints might be different. The images have different resolutions, so you need to rescale them to a common resolution, etc. And there are all these differences which make it really hard to train good model. Nonetheless, models are usually trained on these datasets and compared with each other, and so they're targeted to these kind of datasets. If you compare that with industrial datasets, and for example, here we used the infrared surveillance data, we see that usually or often there's a single class involved. In this case, it's just person detection, or maybe there's a few classes, but they have something in common, so they're more related to one another. Another scene constraint that's often there is that it's a fixed viewpoint and there's also a fixed resolution. In this case, it's 640 by 512. And as all these scene constraints might make it possible to create smaller networks that still reach a good accuracy. And we took this idea and we looked at three different techniques in order to adapt an existing network, YOLO V2 in our example, and make it faster whilst still maintaining that same level of accuracy. If we start with the first technique which we tried, which are some architectural changes, you will see a very familiar slide because we presented this last time as well. The idea here is to replace regular convolutions in our network with mobile convolutions. Regular convolutions can be considered as some kind of 3D operations, whilst the two other convolutions are more like 2D operations. And so the idea is that they require less computations, but they still go over the same information and compute the same kind of information. And so they should be equivalent, but require less computations. And so we tried that and modified YOLO V2 to use mobile convolutions, and you can see the results here. So the results are that if we take a look at the number of multiply accumulate, we see that we reduced the number of operations by a factor of almost 4 times. However, the accuracy also dropped slightly and we lose about 7% validation accuracy on the Pascal VOC dataset. On the infrared surveillance data, which has more scene constraints, we see the same speed up, the same factor 4 reduction in number of operations, but the accuracy is only 1.4% lower. So this already shows this key idea which we had, that academic datasets and industrial datasets usually are not entirely the same, and a model which is designed and developed for an academic scenario can be simplified quite a lot without losing accuracy. However, we still lost about 1.4% accuracy, and maybe your use case or your data set is not as easy as this infrared surveillance data, and you're more towards the Pascal VOC end of the spectrum, and you lose more towards 5, 6, or 7%. And so this would not be acceptable as a loss of accuracy. And so we sought out some ways to reduce this gap in accuracy. And the idea we had here was to upscale the resolution of the output feature maps of our model, because if it has a bigger spatial resolution at the end, the model would be able to use more fine-grained features and thus get a better accuracy. The easy way to do this is to just upscale the input resolution, but then if you, for instance, double the input resolution, you have 4 times more computations as well. And so we needed to find another way to increase the output feature maps. So we looked at the YOLO V2 model and we noted that at a certain point in the model, it concatenates a small feature map with a spatially bigger feature map. And it does so by cutting up the big feature map into 4 parts and stacking them together. What we decided to do opposed to that is to upsample the small feature map, and then you can also concatenate them because then they have the same size. But this results in the output feature maps to be twice as big. Because after the concatenation, we only have 2 convolutions remaining, the computational influence of doing this trick is much smaller than increasing the input resolution. And indeed, if we compute the number of floating point operations, we see that compared to the regular YOLO, if we double the input resolution, we would get 4 times more computation. And our technique, whilst having the same output resolution, only increased the number of computation by a factor of 1.4. Does this yield better results? Well, we just tried it. And if you look at the results here, we can see that it indeed helps. Both YOLO V2 upsample and mobile YOLO V2 upsample got better results than their non-upsample counterparts. And so if we compare our last model, so mobile YOLO V2 upsample with the original YOLO model, we can see that we still have around 1.5 times less computations that are required, and we reduce the gap in accuracy, and it's only 5% lower. Doing the same tests on the surveillance data yields even more impressive results, because their mobile YOLO V2 upsample, whilst requiring 1.5 times less computations, is even better than the original model. We increase the accuracy by 2.3% and require less computations. So that's really a nice thing, because by combining mobile convolutions and the upsampling trick, we managed to get a faster model, which is even better on our use case. And that wraps it up for the architectural changes. And so let's start looking at the pruning techniques. Pruning, not everyone might know what it is, so I'll quickly explain it. The idea of pruning is that you select certain channels of your kernels and you decide to just drop those kernels. And so if we do this on the first example, reduce the number of kernels from 32 channels to 30 channels, then the number of output feature maps also changes. So we need to change all the layers that use that feature map. We need to adapt it as well. And so we need to track some kind of dependency chain. In this linear case, it's really easy. It's just the next convolution which we need to change. But in real networks, this might become a little bit more complex, certainly when there's branching and whatnot. And so we implemented some kind of generic convolutional pruning framework on top of PyTorch in our LightNet library that's able to track all these dependencies. And then we implemented 2 different pruning techniques, normalized L2 pruning and the geometric median pruning. Basically, the difference between these 2 techniques is how they decide which channels should be removed. For L2 pruning, they just compute the L2 norm, and geometric median is some other computation, but I won't go into details here. We use this pruning technique in our pipeline, but there's various different ways to perform pruning, and we most specifically performed hard pruning, which means we really dropped the channels. And so I'll quickly explain how our pipeline works. First and foremost, we start with a trained model, and then we compute the accuracy of that model. It's important to note that we compute the accuracy on a validation data set. In order to use pruning, we need to have a training set, a validation set, and finally a test set, because we use this validation set actively during the pruning pipeline. So it's really important to have these 3 subsets, otherwise you might be overfitting on your test data, and that's never a good sign. And once we computed the validation accuracy of our trained model, we can start pruning. And so we iteratively prune X% of our network each time. So that can be 5%, 10%, 15, 20. That's a hyperparameter to select. And so once we pruned a certain number of channels of our network, we start retraining the network in order to reach the same accuracy as the original model had. So every epoch after training, we check what our new validation accuracy is of our pruned model. And if that accuracy is higher than the original accuracy, and not just higher than the original accuracy, but higher than a certain alpha parameter, so higher by a certain margin than our accuracy, then we preemptively stop our retraining and say, okay, this is good enough. Now we prune the same percentage, so 5% again on our model. The reason we do this little check is in order to not overfit on our validation data. However, if we retrained for the maximum number of epochs and we still didn't reach this upper threshold, then we also allow the network to be slightly below the original validation accuracy. The idea here is that your validation data set is only a small subset, so a minor drop of 1 or 2% on validation accuracy might not be really representative on your entire data. And so we allowed the accuracy to drop slightly below the validation accuracy. And if that's the case, then we also continue on pruning and prune the next model. If it doesn't reach this lower threshold though, then pruning is done, and then we store the final model, which is actually the previous model and not the last model, because that one just failed, so we need to restore the previous model. To give you an idea on how long this takes, training on the surveillance data took up to 12 to 15 hours, but pruning actually took over 2 days. So pruning is quite a slow process, but is it worth it? Well, let's look at the results. And the results show that it's most definitely worth it. So looking at the validation accuracy, we see that it slightly drops. This is this beta parameter which we allow it to drop. And looking at the number of computations, we see that we were able to prune over 50% of the number of computations on all the networks, which is quite impressive. And so our fastest network, which is mobile YOLO v2, is about 10 times faster than the original YOLO v2 network. It requires 10 times less computations. Obviously, it also has about 9% drop accuracy here, but you can choose one of the networks depending on your use cases. So even the original YOLO v2 we reduced the number of computations by over 50% whilst maintaining a relatively good accuracy, only 2% difference between the pruned and the regular network. Doing the same thing on the surveillance data yields even more impressive results. And this shows again this difference between academic and industrial data here. The validation accuracy barely moves, but if you look, you don't even see the rectangles anymore of the number of computations. And that's because, for instance, our fastest model, which is mobile YOLO v2 upsample, the pruned version requires 350 times less computations than YOLO v2, and the accuracy is even better than the original model. So we got a model that's better than the original and requires 350 times less computations, which is really, really impressive. That wraps it up for the pruning part. And so let's finally take a look at the quantization and the benchmarks which we ran on our embedded device. For quantization, we ran benchmarks on an NVIDIA Jetson Xavier, and this time we did not use TensorRT, but we remained with the PyTorch implementation because that was just easier. And as some of you might know, at EAVISE we build a library on top of PyTorch, which is called LightNet, which contains all of our single shot detectors, and as of now also contains the pruning pipeline in order to prune our models. However, we now created a new library, which is called PhotonNet, and PhotonNet also uses PyTorch, but uses the C++ library version of PyTorch, and allows us to use, for instance, multi-threading in order to create more efficient pipelines, which is not really possible in Python. For this test, though, we just used a real simple linear pipeline where we load in the image, we pre-process the image so that it's the right dimensions, then we run the model, then we do some post-processing, and in order to get the bounding boxes to fit the original dimensions of the image. The advantage of PhotonNet, or at least of doing everything in PyTorch, is that we can run this entire pipeline on either CPU, on GPU at 32-bit floating point, or PyTorch also allows to run on GPU at 16-bit floating point numbers. Or we can mix and match and run the pre-processing on CPU and the model and the post-processing on GPU, or vice versa. There's virtually no limits, and it's up to the people who use it to decide what's the most interesting use case. In this scenario, we run everything on the GPU for these benchmarks, and first we run it at 32-bit and then at 16-bit. So let's cut the chase and go to the results. So here you can see the slide which you've seen before with this time it's the test accuracy. As I said before, we now have our final models, so we run the last benchmark on our test, but we can see that the results actually barely changed compared to the validation accuracy, so that's really good news. And the number of computations obviously stay the same because they just depend on the model and not on the data. And so looking at the runtime speed of our model in 32-bit floating point, we see actually a very similar graph to the number of computations, which makes sense. The more computations, the slower the model, albeit slightly more toned down. The difference between the fastest and the slowest model is not as big as with the computations. This is because there's an overhead between the communication from CPU to GPU telling compute this layer, then compute this layer. So we don't get the full 10x speedup. Still, our fastest model here, mobile YOLO v2, is around 3.5 times faster than the original YOLO v2 model. So that's quite impressive. And taking this to 16-bit, yields quite some nice results, which we would expect as well. The models which require the most computations gain the most by going to 16-bit floating point. And if you see the results of YOLO v2 or YOLO v2 upsample, we get a reduction of about 50%. They're twice as fast, but the faster models like the Prunt YOLO v2, which is our fastest, only reduces by a minor amount. Still, all the networks get faster by using 16-bit floating point. And so at the end, our fastest network on the Pascal-Vogt data is the mobile YOLO v2, and it's capable of handling an image stream of 60 frames per second once we add the time of post-processing as well. And the images are 416 by 460. Performing the same test on the surveillance data is also really important and really interesting, because here our results are much more impressive if we look at the pruning side of things. And taking a look at the 32-bit floating point runtimes, we see some really impressive charts here, and the fastest network is actually YOLO v2 upsample and not the mobile YOLO. We managed actually to prune so much of the networks, up to 99% of the channels in the networks were pruned here, that the overhead of having more layers, because the mobile networks have twice as many layers, becomes actually a bottleneck and makes the network slower than YOLO v2 upsample, and the computations are actually less of a bottleneck. And so YOLO v2 upsample here is the fastest network, which was quite fun to see. That means that we actually pruned so much, and it's 15 times faster than the original YOLO v2 network. Bringing this to 16-bit floating point yields the same results as before. The slower networks gain more than the faster networks, but still everything becomes a little bit faster. And again, after adding the post-processing, we get a final result. YOLO v2 upsample, our fastest network, can handle a 640 by 512 image stream at 128 FPS for this dataset, which is quite impressive. To conclude and to reiterate, first, we tried architectural changes. This got us 4 times less computations, but there's some engineering required. It's not an automated way. We needed to do this upsample trick, etc. So not automated, but still it can reduce the number of computations by a factor of 4, which is quite impressive. With pruning, we managed to prune up to 99% of our models, which is really impressive, but obviously it's depending on your use case. If you have a more difficult data set or less scene constraints, you might be able to prune less. Still, on Pascal-Vogt, which is an academic data set and which is considered quite difficult, we still managed to prune 50% of our networks. Finally, quantization can give up to a 2x speedup or slightly less for the fast models, but there's virtually no downsides. When computing the accuracies, we didn't see any differences, which is why I didn't show it here. So there's really no reason not to use a 16-bit quantization. And so all three together, our fastest network was Prunt YOLO v2 upsample. It has a 5% better accuracy even than the original YOLO, and it can handle a 640 by 512 image stream at a frame rate of up to 128 frames per second, and that's in our PyTorch pipeline. If we compare this with the original YOLO v2, which could only handle up to 14 frames per second, that's almost 10 times faster. So these three techniques together really yield some cool results. And what's more is that this Prunt YOLO v2 upsample wasn't even the network with the least amount of computations. And Marianne's team from MICAS would probably be more interested in the mobile YOLO upsample, because there we reduced the number of multiply accumulates by a factor of 350. And so their custom hardware could probably exploit that model even further to get even better results with it. I would like to thank you for your attention, and if you have any questions, feel free to contact us.